Geometric sequences and series. A geometric sequence is one where we multiply by the same amount, what we call a common ratio, to get to the next term. An example would be the sequence 1, 2, 4, 8, 16, and so forth, where we multiply by 2 to get to the next term. Notice that we could have written this sequence as 2 to the 0, 2 to the first, 2 squared, 2 cubed, which means that the general term can be written as a sub 0 times r to the n power. Now that's assuming we start at 0. If we want to start at n equals 1, we could write it as a sub 1 times r to the n minus 1. That one's very common in textbooks for n greater than or equal to 1. In calculus, most often we start geometric sequences at 0. So a geometric series, which we know is the sum of the terms in the sequence, can be written in the following fashion. The sum from 0 to infinity of our sequence, or if I wanted to start at a 1, for example, I could do the sum from 1 to infinity of my first term, a sub 1 times r to the n minus 1, etc., etc. And recall that when we're doing sequences and series, unless otherwise stated, we assume that these are infinite. So I have two claims I want to make. The first claim is that a geometric series will converge under certain circumstances. In fact, a geometric series will converge if the ratio is between negative 1 and 1. And I'm going to put an extra f there. If you haven't seen that before, it stands for if and only if. Very often we write this as the absolute value of r is less than 1. Notice it's strictly less than 1. What if r equals 1, for example? Let's do a couple quick ones. If r equals 1, and let's say we have just simply 1 to the n, that's 1 plus 1 plus 1 plus forever, and that certainly doesn't converge to a finite number. If we did r equals 2, like the sequence we showed above, if I start at 0, then the sum will be 1 plus 2 plus 4 plus etc. And certainly that does not converge either. Now I haven't shown the fact that the series will converge between negative 1 and 1. I will try to convince you of that in just a bit. But I need to make the second claim before I talk about that, which is if we have a geometric series. So we got to make sure that we have a geometric series to start. And we know that the geometric series converges. That is, if the ratio is between negative 1 and 1. Then we know the infinite sum of that geometric series. In fact, it's given by the infinite sum is, and I'm going to write it like this. I'm going to write it as first term over 1 minus the ratio. A lot of books show this as a sub 1 or a sub 0 or something over 1 minus the ratio. But I like to write it as the first term over 1 minus the ratio. Now, I'm not going to do any examples here. Not yet, anyways, because I want to try to convince you that these claims are true. And if these claims are true, this is the foundation for some very, very powerful mathematics, which we're going to get into in the next few videos. So let me set up a quick picture for us. And I'm going to draw two lines that are going to intersect in the first quadrant. The first line is going to be the line y equals rx, where r is between 0 and 1. The second line is going to be the line, and I'm not going to draw quite to scale here, but just get a picture here. The second line is going to be the line y equals x minus 1. Now convince yourself that these two lines must intersect, and they must intersect in the first quadrant. And I'm going to call that intersection point just x. I'd call it like x sub 0 or something, but we'll just call it x. Now, if you weren't sure of the reason why these two lines must intersect, is because this second one that I drew, y equals x minus 1, has a slope of 1. And the first one has a slope between 0 and 1. So our goal is to find where they intersect. Now, if they intersect, then the y values must be equal. So if I do a little bit of work, I get 1 equals x minus rx. We can factor out the x to get 1 equals x times 1 minus r, and then I'll switch sides because I like the x on the left. And I get x equals 1 over 1 minus r. Now, before I go on the second part, that sort of looks like my claim 2, doesn't it? Now, we want to find x in a different way. So I want to find out how far it is from the axis to x. So let me change colors for us. Hopefully we can see a little bit better. And we're going to do this in parts. Let's look at that first length there. My claim is that length of that first part is 1. How do I know? Because y equals 0 when x equals 1 for the bottom line. Now I'm going to find this length. This length is not going to add up to get to the x value, but it's going to help me find it. And my claim is that this length here is r. There are a couple ways to figure out why it's r. One is by plugging x equals 1 into that equation there. But I'm going to think about it a different way. If this length here is 1, and the slope of this line is r, where the slope is y over x, then the y value must be r. Now let's figure out the length of the next horizontal piece. And my claim is that length is also r. The way I determine that is by looking at the slope of this line, which is 1. So if slope is y over x, or change in y over change in x, and the y is r, and the slope is 1, then the x must also be r as well. So I'll write that over here. So I know that delta y over delta x, using my second line, is 1. I already knew that delta y was r, so what does delta x equal? Well, it has to be r as well. And I'll keep doing this. Let's do the next vertical segment. And I'll write this one up here, where I know that delta y over delta x, using the top line, is r. I already found from here that delta x is r, which means delta y must be r squared. But using a similar logic, that horizontal segment must also be r squared as well. And if I continue on using that logic, I get that x must be 1 plus r squared plus r cubed plus forever. Now, this is not a proof. This is what we call a convincing argument. You might say, well, if I keep doing these segments, I never really reach x. But here's the counter to that argument. You know you have to reach x, because the lines definitely intersect. Now, the x that I found using slopes makes a geometric series whose first term is r. The x that I found, setting the equations equal to each other, gave me 1 over 1 minus r. Which means that 1 over 1 minus r equals 1 plus r squared plus r cubed forever. Which is my second claim. Now, why must r be between 0 and 1, or negative 1 to 1 is what the full claim was? Well, what if r is bigger than 1? Or even if r equals 1? It's clear that the sum goes to infinity and does not go to a finite term. Now, I have not proven the claim. I have simply shown it in the most simplest case and for positive r's. There's a very similar approach to show that this also works for r between negative 1 and 0. I won't show it here. Perhaps in a later video. But here's the thing that I want to talk about before I stop. What if I think of these as functions? Let my function f of x equal 1 over 1 minus x. We call this a closed form function. Basically, I can plug in any x value and get an answer. But under certain circumstances, and this is the power of math that we will explore, that this closed form function is exactly the same as its infinite series. In the next video, we will talk about why this matters and how we can use this.